Okay, here's a problem that my friend Jean wanted me to work out. And it says here that a steam reforming of methane produces synthesis gas, a mixture of carbon monoxide and hydrogen, which is the starting point for a lot of things in industry. And it says a chemist studying the reaction fills a 75-liter tank with 5.9 moles of methane gas and 4.7 moles of water vapor. And when it finally does get to equilibrium, then it tells us that it has carbon monoxide gas at this number of moles. And it's asking us to calculate a concentration equilibrium constant for this particular reaction. Okay, well, let's get the chemistry right first. Okay, and so I do have methane plus water, the steam, and those are both gas, is going to come into equilibrium here with carbon monoxide and with hydrogen gas. Okay, so we wrote the chemistry here. Let's make sure we balance things out here. So 6 hydrogens, put a 3 right there, and that should do it for us. So this is the chemistry here. And let's also, we can write, since those are all gas, and I'm lazy, so I'm only put it on that one. So these are all gas, so we can write an equilibrium, that the equilibrium is going to be equal to concentration of CO, concentration of H2 cubed, divided by concentration of CH4 times the concentration of H2O. So again, these are all in concentrations. And so when I do that, I have to realize I'm given moles here, but I am given a volume, and so I'm going to have to do that math. I hate problems. I just don't do the math for me. But anyway, let's go ahead then and let's do our ice tables. That's one way to do it. It's not the only way, but it's, since we're doing ice tables, and let's go ahead and do that. So we have initial change in equilibrium, and then I always like putting my reactants here first. That's CH4. That's going to be H2O. Leave yourself plenty of room. CO, and then H2. Well, it tells me that my carbon monoxide gas at equilibrium, I start off with none here. Okay, but it does tell me at equilibrium, then this is going to be 4.2. Now, since I know that, I'm going to use X here to represent the change. We know that it's not going to be 4.2. It's going to be 4.2 divided by the volume, which is 75. And so when I do that math, then I get here 0.056. Okay, so that's what I get, 0.056. See, I almost messed up and didn't take the molarity of that, or the volume. Okay, so I'm just going to call that change X, and I know that X equals 0.056, but my ice table can help me establish some of these relationships. And so the initial of CH for the methane is going to be the moles of methane divided by the volume, because I need to get that in concentration, right? And so when I do that, I get 0.0787. Okay? And for the water, when I take 4.7 divided by the volume, then I get 0.0627. Okay, remember the change here helps me with stoichiometry, and I get this change here by looking at the equation. And I know that if I start out with only these two, it has to move to the right, the equilibrium does, meaning that these are going to go down. It's going to be a minus X, because it's a 1 to 1 stoichiometry. It's going to be a minus x as well because it's a 1-to-1 stoichiometry. And it's going to be 3x right here because it's a 1-to-3 stoichiometry. Okay, so when I come down to equilibrium, I get 0.0787 minus x. I get 0.0627 minus x for H2O. I already know that x is 0.056, remember, because it gives me equilibrium moles, which I then divided by 75. So I know that right away. And then this is going to be 3 times x for the water, for hydrogen right here. Okay, 0 plus 3x is 3x. Okay, these are my equilibrium concentrations, so if I can calculate each of these, I can just put them into my equilibrium equation right here and solve. Okay, so since I already know that x is 0.056, okay, then I can just sort of say, okay, I got CH4 here, I've got H2O here, I'm just making a little table for myself, I've got CO right here, and I've got H2. So for CH4, it's going to be 0.0787, 0.0787 minus x. X is 0.056, 0.056, and that is going to give me 0.0227. Okay, the H2O, the starting concentration, is 0.0627 minus x, which is 0.056, and that's going to equal 0.0067. The CO we already know is 0.056, and H2 is going to be 3 times 0.056, which is going to equal 0.168. Alright, so I'm just going to plug things in right here, and I can see that I'm running out of space right here, so I can just scrunch this in. So K equilibrium is going to equal the concentration of CO, which is 0.056. It's going to be 0.056 times the H2 concentration cubed, 0.168 cubed, divided by the concentration of CH4, which is 0.0227, times the concentration of the water, which is going to be times 0.0067. So when I do that math right there, then I get, with 2 sig figs, 1.8, which is my equilibrium constant. So you can use ice tables. Since we're doing ice tables, I would suggest just to do that. But the trick of these is to remember that it does give you the equilibrium number of moles, which you can then convert to molarity right here. And if you establish that as your x and work your stoichiometry in your ice table around that, then you should be able to follow this and do this. And there's little variations here or there, but again, just establish your x and work stoichiometry around that.